Hello, my name is Monica and I'm going to be giving a general sense of the catalytic cycle of cross-coupling. So first, let's begin by drawing the cycle with Ln being some number of ligands, like this, and then we have an R1 group with a halogen. We're going to have that blank, and then we're going to have a metal within the halogen and a metal within R2 group. And then this one will also be blank. So the ligands will be a stable resting state in that palladium 0 species, so this one. And the palladium 0 species will normally be an 18 electron species, so we can write that down here. An 18 electron species. And it will need to lose a group, so need to lose a ligand group. Or just a ligand. And this allows the first reaction partner to bind to it. So here we're going to have the oxidative addition reaction. Some organic species with a leaving group could be a halogen. So this X here, we're going to say is the halogen. And it's a leaving group because it's something that the carbon halogen bond can act as a leaving group. So this is also a leaving group. So first, palladium needs to get oxidized, which is why it's an oxidative addition reaction. So we can also write that down there. That this palladium gets oxidized. And then part 2 for this reaction is the R1X, or this, this reaction. This adds to the palladium species by breaking the bond in half and attaching it to the palladium species. So what I'm saying is this R1 group with this X, this breaks in half, and each side, this and this little tiny thing right there, will attach to the palladium, in which we'll get the ligand with the palladium that's attached to the R1 and the halogen. But palladium will now become palladium 2 instead of 0. And this reaction is fairly reactive. So once again, it's an oxidative addition because the palladium gets oxidized and then these groups get added. So then we move on to the next step, in which this is called transmetallation. And this is an organometallic reagent. So we're swapping the metal with the palladium 2 that we got right here. So for this one, we're swapping palladium 2. Oh, I'm swapping the metal, my bad. The M, or the metal, with the palladium 2, which then gives us this metal halide in the same step, right? Which will give us the ligand with the palladium with R1 and R2. So this attaches to the metal, which gives us the metal halide right there. And then our next thing is the reductive elimination. So palladium 2, in this case, palladium 2 gets reduced to palladium 0 because we want to come back to this. So that's why it's called the reductive, the reductive part. So for the elimination, we're eliminating the two groups. So R1 and R2 will be eliminated from the palladium center, which will bring us back to our original thing that we started with. So R1 dash R2 are separated. Once again, we could just write here elimination. We're eliminating the two groups attached. To the palladium center. And that gives us the elimination part. So we have the reductive and the elimination part right there. And in the end, we get this active catalyst. And I just wanted to say that the palladium is very common when you're cross coupling some of these reactions. So there's other types that you can use. And I also wanted to go back to the transmetallation step right here to identify some of the other reactions within that can happen. So we can draw an arrow over here. There are 4 types of couplings that can occur. So we can have in our, the R2 or prime with zinc, and that will be called Negishi coupling. And then if it's an R2 with tin, or this, it'll be a steel coupling. If it's an R2 with copper, it'll be Sonogashir. I might be butchering it. Coupling. And then for the last one with the R2 group, if it has any boron, and it could be that, or something like that, it'll be the Suzuki coupling. And you can tell which coupling to use given, if it's either zinc, tin, copper, or boron. So just, be on the lookout for that. And some, more in depth for the boron, you have some options. Some boron compounds for Suzuki include, this R. We're going to generalize it here, so it R with the boron with 2 other R groups. This is organoborane. Then there's also this, and this is called boronic ester. And finally, we have an R group with the boron with 2 OH groups called boronic acid. So, these are just 4 different types of coupling reactions that can occur during this transmetallation step in the catalytic cycle. And then we're going to go on to talk about NAS reactions, or better known as nucleophilic aromatic substitution. So there's 2 types. So first we are going to talk about NAS1, which is the elimination, addition, reaction, and I'll show you the mechanism for that. So let's pretend we have this. There's an H here. We have this, and we're gonna add NH2 to it. Like, what do we get? So I'll show you the mechanism for that. Okay, so first, draw it again. You have this NH2 here. And this N is going to attack the hydrogen, and then the hydrogen is going to give back its bond to that carbon. And then we get this. And then the boron also leaves here. Bromide, my bad. Leaves. So this bromide leaves. And then we get that, which could then be the elimination part of our reaction. Then we have more NH2, which will attack this carbon here, and then that carbon is going to go back there. And then we have this carbon, and this NH2 is attached there. Then we have this NH3 here, which will ultimately give us the product of this. And then this part right here is addition. So that's why it's called the elimination, because you have that there, the addition there, reaction. And then for NAS2, it's the opposite, basically. So it's addition, elimination, reaction. So if we have this substance, for instance, with negative CH3, what would we get? Show the mechanism here. Also forgot this NO2 right there. Once again, draw it out. Then we're going to have this OCH3. And then this this oxygen is going to attack this carbon because this is delta positive and then this is delta negative. So then this double bond is going to go here, attack there, which will give us this O CH3 here. The F there. This carbon looks like this. Our ring looks like that, and then we have our NO2. Also just wanted to point out that this is aromatic, and then this is non-aromatic. And then we're gonna go like this, and then they're just gonna start rearranging where those lone pairs go there. This will attack this nitrogen. Then we'll get this. And this carbon negative there. Once again, we're still rearranging. This double bond's gonna go there. These lone pairs are gonna go there to give us this ring. And the lone pairs are over there this time. And then we still have our NO2. I'll just rewrite it like that. Then these lone pairs and attack over here, which will then make this F group leave, which will ultimately give us the product of this. So going back to naming it, this will be the addition because we added this OCH3 group. So addition. And then this here would be the elimination because of the F leaving. And I also wanted to point out that this group right here is an electron withdrawing group. So over here, just so you know. And yep, that's the end of this video. Thank you.